Hey everybody, welcome back to another round of astronomy, and yeah, let's get going. Today we are going to progress from our Kepler's laws into the new going model for how the universe works. Now bear in mind, Kepler was able to take Brahe's data and distill several patterns that he observed about the universe. However, he was not able to say why those patterns are being followed. So that paves the way for Isaac Newton to come in and describe a new conceptualization of the universe that helps us get an idea about why the patterns are being followed in the first place. Now, let's bear in mind there are a couple of other lingering questions out there. The one that I'll highlight for you is Tycho Brahe and his observation of a comet. Recall that in that discussion, Tycho Brahe was able to measure the distance to a comet, and he was able to verify that it indeed was something traveling through space. And even more so, it was passing through the celestial spheres, or excuse me, the glass spheres on which each of the planets was supposed to be pasted. And so there's this question, this underlying question about how do planets move in space? What is actually keeping the planets up in the universe rather than them falling into the sun, for example? Similarly, what's keeping the moon in orbit around the Earth? They don't have a good conceptualization of what that mechanism is. So Newton comes in and he gives us a new way of conceptualizing the universe. Of course, he isn't alone in this endeavor, and he has this wonderful quote saying, "If I have seen further than others, it is by standing upon the shoulders of giants." Excuse me. So, we'll start off with this, the dreaded P word. I say not to fear. I know that I'm slightly biased in this, but not to fear. Let's go ahead and talk about something else. How would you define sociology? Okay? Yeah, you got an idea? Okay. And I haven't had anybody yell at me yet about this, so if I get this wrong, I apologize, but 6 years running, I'm okay so far. Okay? So, let's go. How would we define sociology? I'm guessing that you've said something about people, or maybe even groups of people, or maybe even communities, something along that line. You've indicated that you're studying people or a person. Okay? And then on top of that, I would imagine that your definition somehow incorporates the interaction between people. So you might be studying a husband and wife and studying their interaction, okay? Like a small family unit. Or maybe you're studying parents and children, right? And that interaction. Or maybe you're studying Hanover College with Hanover the community. Okay, so groups on how they interact. Okay? And of course, there's multiple ways that these interactions can occur. When I say interaction, part of it is like what I'm doing right now. I am speaking to you, verbal interaction, verbal communication. Of course, this is one-sided right now, right? I'm speaking to you, but you can't speak back to me. That's a form of interaction. And that's different than, say, something like when I call you up on a phone, where it's a two-way interaction. Or maybe I text you so that you don't get the voice inflection, you just get the straight words. Okay? Or there's other interactions that I use. Okay? Physics is about studying interactions as well. It's just the question about how does an object, which, not living, no sentient structure or anything like that, this object doesn't know anything, okay? How does this object know that this object beneath my feet is even there? And how do we know that there's an interaction? Well, if I let go of this object, it somehow is communicating with this earth, that object, and that communication is telling the pen to do something. Okay? So that's really what physics is doing. We would like to know, how do inanimate objects interact with one another? Okay? And that is the framework that Newton proposes to us. he tells us, he gives us a model about how we can tell that an interaction has occurred and what the object will do because of that interaction. Okay? Okay, so let's get into it. Newton gives us a conceptual framework to understand how we know that an interaction has occurred and what an object will do in response to that interaction. He poses it as Newton's 3 laws. Now, I'm going to give you the translated forms of these. If you look it up in the book, like the first law is an object will continue in motion in a straight line at constant velocity unless acted upon by another force. I'll say forces change an object's speed or direction, and or. So it could change the speed, it could change the direction, or it could change both. Okay? So again, notice this, we're going to introduce this conceptualization. We haven't really said what is a force. We've introduced an idea about a force, we've used the term, and we've stated how an object responds. Okay? Incidentally, which thing are you actually going to observe? Are you going to observe the force, or are you going to observe the change in speed and direction? Yeah, good. You can notice this. This is the observable. And this is what we are going to infer. Okay. If I see an object change direction, then there must be a force acting on it. Okay. That's what Newton's law is going to, that's what we're going to assume when we apply Newton's laws. Okay. Number two is best written as an equation. And I'm guessing if I say, quick, give me an equation from physics. I'm guessing that you gave me one of 2 equations. By and large, I want to say like 95% of the time I get these 2 equations. I either get E equals mc squared, which we will use later, or I get the one I'm thinking of, F equals ma. Okay? Force, F equals the force, m represents the mass of the object, right? And A represents the acceleration. Okay. So Newton's second law gives us a quantitative way of observing the motion of the object and saying quantitatively, numbers, what the size of the force is acting on the object. Okay? Third one, I call it sweet revenge. You've probably seen it. A force, object A acting on object B exerts a force. The same force is exerted by object B on object A in the opposite direction. I just call it sweet revenge. Okay? If one object pushes on another object, the second object pushes back on the first. Okay? Sweet revenge. Let me try to develop a little bit more intuition about these 3 laws. Okay? So here's the first one. Imagine I have a ball. Okay, I've got ball 1 and ball 2. Okay, they are both moving at the same speed, so that's indicated by the arrow. Usually we use the word velocity, so you'll see usually v here, but they're moving at the same speed. Okay, ball 1 moves at the same speed as ball 2. They both have a ramp. Okay, question for you. If I have, and you notice the first ramp has some steep angle, the second ramp has a less steep angle. And the question I have for you, what happens to the distance traveled by the ball up the incline? Okay? In other words, if I'm comparing ball 2 and ball 1, let's draw those the same. Okay? What can you tell me about the distance traveled up the incline? You got it? Good. Yeah, so if the ramp is steeper, okay, ball 1 will travel some distance. Ball 2 should travel a much longer distance, right? As the angle of the ramp decreases, the ball travels a longer distance up the ramp. Okay. Now let's imagine As I keep decreasing it, the ball is going to travel further and further and further up the ramp. What happens if I decrease it until the angle of the ramp is 0? What will the ball do? Yeah, you get it? Right? It'll just continue on forever. Right? So here's a profound shift that Newton has actually proposed. Okay? Prior to Newton, the idea was that forces are required for objects to move. Okay? In order for an object to move, there must be some force continuously acting on the object. Okay? Newton came in and said, oh, nay, let me flip that idea around. Okay? An object will continue to move on its own accord unless acted on by a force. Okay? Good? Yeah, keep convincing yourself of this. Keep thinking about this. But it is a radical change in our conceptualization of how objects interact. Okay, good. So that's the first one. Next question. Let's say I have a cart that is pushed in the same direction as it's moving. So I'll draw a cart here. So we'll say, okay, there's a cart, it's moving to the right, and I decide to also push it to the right. I will push it to the right, put a force on it. What happens to the speed of the cart? Yeah, it speeds up. Good. Right? As it rolls one way, I keep pushing it, it will speed up. Corollary question. What happens if I push it in the opposite direction? So if it's moving to the right and I decide to start pushing it to the left. Yeah, good. This is like the ball rolling up the ramp, right? If the cart's moving to the right and I start pushing it to the left, the cart is going to slow down. Eventually, it will stop. And then all of a sudden, it will start speeding up going the other direction. And now my force is pushing in the same direction and it will start speeding up. Okay? Good. So we've got one idea. Is that, okay, the overall idea of force will cause the cart's speed to change. If the force is in the same direction as the motion of the cart speeds up. If the force is in the opposite direction, the cart will slow down. Okay. Well, how do we change the direction of an object? Here we go. Okay. So let's say we have an overhead view. So we'll say overhead view. Okay. And let's say we have a hockey puck on ice. And I wish the hockey puck to follow the dotted line. Okay. First of all, we should say, if we want to hit the hockey puck, so let's assume it's already initially moving. Okay. First of all, where do I hit the hockey puck? At what location along the path? Yeah, you got it. It's right here, right? Right here at this location, I hit the hockey puck, right? I notice that it changes direction. A change in direction indicates that a force has been exerted. Okay. Next question. So I need to hit the hockey puck right here when it reaches this location. The next question, which direction do I need to apply the force? You got it? Yeah, well, let's eliminate some ideas. If the hockey puck is moving towards the top of the screen and I hit it towards the top of the screen, what will change? Yeah, good. The velocity, right? If I hit it going that way, it will speed up. Well, what happens if I hit it going this way? Good, it'll slow down. Does that mean it changes direction? Yeah, no. So A and B are immediately out. A and B would speed up and slow down, respectively, the hockey puck, but it won't cause the hockey puck to change directions. Okay, so we're done with that. So then the question is, we have to figure out, is it C or D? Well, which which one will make it go to the right? Yeah, if I want it to start moving towards the right, I better hit it going to the right. Yeah, good. So we have C is actually the direction that we... So now we have two ideas. Okay. We have two ideas. Okay. If there is no force, the object will continue moving indefinitely in the same direction at the same speed. Okay. If there is a force, either parallel or anti-parallel to the direction of motion, the speed changes. It either speeds up or slows down. Okay. If the force is perpendicular to the motion, then the object changes directions. And of course, you could have a object, that's moving in some direction, and you could apply a force in some other direction that's neither parallel or perpendicular. What do you think happens to the speed? Good. The speed changes. It'll speed up. How about the direction? Yeah, also changes. So you could think of this force as having some perpendicular component and some parallel component. I'll call it F1 and F2. And the perpendicular component will change the direction of the velocity. The parallel component will change the speed. Yeah, so you can do not only one or the other, but both simultaneously. Okay, good. So that's all I have to say about the first law. Again, just some qualitative, heuristic arguments. Let's go ahead and talk about the second law. Okay. So let's say this. You have two shopping carts, both of which are empty, and you're having a shopping cart race. How this race works, you are going to give the shopping cart a push, and then whichever shopping cart crosses the finish line first wins the race. Okay, so you're not going to continuously push it. We're going to say one push and that's it. Okay? So here's the question. Okay? Cart 1 is pushed by Captain America, whereas Cart 2 is pushed by Mr. Steve Rogers. Which cart's going to win the race? Yeah, you got it? Good. I'm sure you got this one, right? Yeah. Well, I don't know. I don't know about you, but I think Mr. Captain America is going to be able to exert a larger force on his shopping cart. Therefore, shopping cart 1 is going to fly across that finish line first. So the idea here is that if I apply a larger force, I'm going to get a larger acceleration. In technical terms, we would say the acceleration is proportional to the force. Larger force, larger acceleration. Okay? Okay, that's step one. How about this one? Okay? We are again going to have a race. And this time, Captain America is going to push both shopping carts. Okay? But shopping cart 1 is full of groceries, whereas shopping cart 2 is empty. Okay? Captain America needs a lot of calories to, go out and save the world. Okay? So here's the question. Which shopping cart wins the race? Yeah, you got it? Yeah, good. I figure, okay. All right. Well, here, since both shopping carts are pushed with the same force, the shopping cart with the larger mass is going to have a lower acceleration. All right. I push. Okay. So we say that the acceleration is inversely proportional to the mass. As the mass, if the force stays constant and the mass increases, the acceleration must decrease proportionally. Okay? So we can take those two heuristic arguments and put them together into a single equation. Okay? Well, let's double check. If my mass is constant, okay, so this is constant, shopping carts are both empty, and my force goes up, my acceleration must go up. Okay? Captain America pushing the shopping cart is going to beat Steve Rogers pushing the shopping cart. That's the first example. Well, the second one is the force is constant, but the mass has increased. So that means if the force is the same, but the mass goes up, that means the acceleration must have gone down. So that's the inversely proportional. Yeah, so this just puts it all together in a nice package for us. Sweet revenge. Now, heuristically, I don't really have a great way of showing you the sweet revenge. But there's plenty of examples out there. For example, here we go, SpaceX, Elon Musk's company. How do rockets really work? In fact, if you're a swimmer, go to Southwestern, jump in the bottom of the pool, sink to the bottom, okay, and ask yourself, how am I going to, let's say you're not touching the bottom of the pool, okay? You're somewhere in the middle, but ask yourself, how am I going to get back to the surface? A rocket ship works the same way. Okay? If you're, well, okay, maybe not a swimming pool. Let's say you're in the ocean. Okay, you're beneath the surface. You need to get to the surface. How do you get to the surface? Well, you take your arms and you push down on the water around you. Okay? Well, the law of sweet revenge, Newton's third law, if you push down on the water must push up on you. And so that motion of pushing down on the water propels your body upwards. A rocket ship works the same way. Okay? What do you see right here? Down here at the bottom, this big flame, what are you actually doing? Why do we do this? We are taking air and pushing it downwards. This is the rocket pushing down on the air behind it. Okay? And because of that, the air pushes up on the rocket. And that's what launches the rocket up into space. Okay? And a lot of forms of propulsion work like this. If you're thinking about a boat motor, okay, same idea. Boat motor pushes water to the right. That means water pushes the boat to the left. That projects the boat forward. Okay? Or an airplane, a jet engine works the same way. There's a big fan blade. Air comes in, the fan blade pushes the air out the back, and because of that, the air pushes the plane forward. Archimedes had this wonderful quote, "Give me a lever long enough and a fulcrum to which to place it, and I shall move the world." I say, oh, nay, that's wrong. You don't need a fulcrum or a lever. You can just jump up and down, right? You are exerting a force on the world, and that is causing the world to accelerate. Just jumping up and down. No. Okay, so somebody will ask, no. Even if you got everybody in the world on the same location and jumped all at once, no, it's not. You're not going to accelerate the Earth very much. Okay? And you could say, why? Well, this Earth is huge. About 6 times 10 to the 24th kilograms. Okay? Huge mass, whereas a person will be rather generous. Let's say that they're 100 kilograms. Okay? So the force of the person on the earth, the force of Greg on the earth, right, is the same as the force of the earth on Greg, per Newton's third law. So equal force acting on Greg and the earth. The earth is much more massive, which means what can you tell me about its acceleration? You're thinking about Newton's second law. Yeah, it's going to be minuscule, right? Yeah. This is a full shopping cart. This is an empty shopping cart, right? And so the full shopping cart will have a really low acceleration. The empty shopping cart will have a high acceleration. So you see Greg accelerate, right? He jumps up and down when he hits the earth. You can visually see him accelerate. He goes from moving to stopped. But the earth, you barely see the acceleration because it's so small. Essentially zero. Okay? Yeah, let's get some questions here. Okay? Question. Car hits a wall. Which experiences the larger force? The car or the wall? Yeah, be careful again, right? You got it? Yeah. What does Newton's third law tell us? The force of the car on the wall is the same as the force of the wall on the car. So the two forces are the same. Okay? Yeah. Okay, good. You say, but wait, Greg, something's different. I know something's got to be different. And yes, I agree. Let me ask the corollary question. Okay? The corollary question. Which object undergoes the larger acceleration? Yeah, okay. Now that's where the difference is again. It's the same thing as previously discussed on the last slide. Same force, the wall has a much larger mass than the car, which means the car will undergo the larger acceleration. Okay. So you got to be a little careful there. Yeah. Be careful. It is common to mistake the acceleration for the force. Okay. I see an object accelerate. Excuse me. This object undergoes a larger acceleration. It must have the larger force acting on it. That's the common. Be careful. Okay. Okay. And that's all I have. Okay. Law of sweet revenge. So again, highlighting, Newton gives us a way of conceptualizing the interaction between objects. You notice that we have observables, objects, speed, and or direction. The observable here in second law would be the acceleration. Okay? We use those observables to infer that there is a force acting on the object. Okay, okay, good. I'll leave it there. Okay. But next, we're going to discuss one particularly helpful force in the context of astronomy, gravity. So that's where we're going. I thank you for your attention. Keep up the good work. I'll see you next time.